In this segment, we will discuss Learning Objective 2, which is compute solutions to future value and present value of single sum problems. We begin our discussion by illustrating applications of compounding and discounting a single sum, usually known as an amount of $1. There are four important variables in a single sum problem. One is present value, future value, interest rate per compounding period, and 4, time period or number of compounding periods. If you know any 3 of these variables, you can solve for the 4th one. The interest rate per compounding period is the annual interest rate divided by the number of times per year that interest compounds. For example, if you are earning 8% interest compounded quarterly, then the interest rate per compounding period is 2%. That is your 8% divided by 4 quarters. The number of compounding periods, which is n, is the number of times per year that interest compounds times the total number of years for which a present or future value is computed. For example, if you are holding a 5-year note receivable that pays an interest quarterly, then there are 20 compounding periods. That is 5 years times 4 quarters. We begin by solving for the future value and illustrating various techniques to solve each problem. We will solve most examples using 4 techniques, and they are the formula solution, the factor table solution, the spreadsheet application solution, or the financial calculator solution. For the future value of a single sum, we know the present value of a single cash flow, the interest rate, and the number of periods, and we need to compute the future value. Consider a single bank deposit with $100 left on deposit for 1 year at an interest rate of 8%. And if you look at Exhibit 7.4, we show that. Consider a single bank deposit with $100 left on deposit for 1 year at an 8% rate of interest. To compute the future value of a single sum, we compute interest 1 period at a time and determine the new principal plus interest balance at the end of each period. However, this approach is quite burdensome, particularly for problems involving many periods. A less cumbersome approach is to restate the problem using the time value of money variables defined in the previous section using the formula that you see here, which is where the present value, where PV is the present value. And of course, you know that FV is the future value, while the interest divided by the year is the interest rate per compounding period, and N is the number of compounding periods. Note that the future value is directly related to the rate of interest. That's the interest divided by the year, and the period of time, which is N. And you'll see in the next slide how we illustrate the annual compounding in 7.4. So here in 7.4, there's a problem. Solitude Company invested $10,000 for 10 years at 8% with interest compounded annually. Solitude will receive the entire amount, which is the principal plus the interest, at the end of the 10-year period. So what is the future value of this single sum using the formula approach? So we use the formula in equation 7.2 to solve for the future value. So the future value is equal to the present value times 1 plus the interest over the year and N. So the future value is 10,000 times 1 plus 0.08, which is the interest rate, and 10 is the number of years. So the future value is 10,000 times 2.1589. So you get the 2.1589 by multiplying 1 plus 0.8 to the 10th power. So the future value is $21,589. So the future value of the single sum investment is $21,589. Here in this problem, Solitude Company invested $10,000 in a 10-year investment with a stated rate of 8%. Interest is compounded quarterly. Determine the future value of this investment using the formula approach. So the present value is $10,000. The relevant interest rate is 2%, which is the stated rate of 8% divided by 4, because there are 4 periods per year. The number of compounding periods is 40. And you arrive at 40 by multiplying the number of years, which is 10 years, times 4 periods per year. So you have the future value is $10,000 times 1 plus 0.02. Number of number of periods is 40. And then the third line, you see the present value is equal to 10,000 times 2.20804. And the future value of the 10-year investment is $22,080.40. We can also solve future value problems by using factor tables. A factor is a number derived from a combination of an interest rate and a compounding period that can be multiplied by an amount to obtain the value needed. Instead of using the formula, the factor is a shortcut to compute the needed value. To illustrate, let's develop the future value of $1, compounding factors using the future value formula for equation 7.2. If n is equal to 40, interest over year is equal to 2%, and the present value is equal to $1. Then the future value is future value equal present value times 1 plus I over y to the n power. So you get 2.208 0.04 equal 1 times 1 plus 0.02 to the 40th power. So with a deposit of $1, the future value after 40 periods, when the interest rate is 2%, is equal to $2.21 rounded, as you see in this slide. Table 7A.1 in Appendix A presents the complete set of compound interest factors for future value of $1 factors for solving future value problems. Rows of the table represent the number of compounding periods. Columns have the interest rate per period. The amount presented in the cell for each row and column is computed from equation 7.2. It is the factor for a future value of $1 for the given interest rate and number of periods. In this excerpt in Exhibit 7.5, this is the same table that you would see in Appendix A. So to find out the information, you would use the 2% column and then search down the 40 period row to locate the factor 2.20804 that we derived using the formula. Again, this is the same table that you would see in Appendix A. The factors in Table 7A.1 illustrate that the future value is directly related to N and I over Y. We can now use the factors from Table 7A.1 in Equation 7.3 to solve single-sum future value problems. Future value is equal to present value times factor using this table, where factor in 7A.1 refers to the factor that can be found again in Table 7A.1. To solve for the future value, you find the factor that is in the row for the number of compounding periods and the column for the interest rate per compounding period. Then you would multiply this factor by the present value to obtain the future value. And in the next slide, we'll see how it's demonstrated using the table approach. Here's the problem. Solitude Company invested $10,000 in a 10-year investment with a stated rate of 8%. Interest is compounding quarterly. Determine the future value of this investment using the table approach. So we use equation 7.3 to solve for the future value. We know that the present value is $10,000. The relevant interest rate is 2%, which is the stated rate of 8% divided by 4, because there are 4 periods per year. The number of compounding periods is 40. And it's because 10 years times the 4 periods per year is 40. In Table 7A.1, you look across the columns to find the interest rate of 2%. And then you go down the rows to find 40 number of periods. And you should see in the cell, the factor is 2.20804. Here you see the formula that's used to arrive at the future value using the table approach. So the future value of the 10-year investment is $22,080.40. Here's this table that you would actually see in Appendix A. You're looking at the column, which is highlighted, which is 2%. You go down to the row that has the 40 periods, and the factor is 2.20804. Now, using a spreadsheet application such as MS Excel, it is another way to solve future value problems. The future value function in a spreadsheet cell is in this slide. You have the equal future value, I over Y, then you have N, payment, present value, then type, okay? So we know that I over Y is the interest rate per compounding period. N is equal to the number of compounding periods. PMT is the amount of periodic payments. PV is the present value, and the type will be 0 if the payments are due at the end of the period. And we call that ordinary annuity. And if the payments are due at the beginning of the period, we would use 1, which is also called the annuity due. So for the future value of a single sum, we put a 0 in the third position because there are no periodic payments. Because the type defaults to 0, we do not need to include the last variable as long as the payment occurs at the end of the year. In the spreadsheet examples, we use the convention of designating borrowing or receiving payments as cash inflows and lending or investing money as cash outflows. In the time value of money spreadsheet computations, cash inflows are positive values and cash outflows are negative values. In the next slide, in example 7.7, will illustrate the spreadsheet approach. The problem here, again, is Solitude Company invested $10,000 in a 10-year investment with a stated rate of 8%. Interest is compounding quarterly. Determine the future value of this investment using the spreadsheet approach. So to solve this, we put 40 in the N because it's 40 periods per year for 10 years. I over Y is equal to 2%. The stated rate is 8% per year with interest compounding 4 times per year. That's how we got the 2%. The present value is minus $10,000, and the payment is equal to 0 because there are no payments in a single sum problem. So the future value is computed in the spreadsheet as $22,080.40.